Hello. So this talk is about ZK-SNARKs, and it's probably fair to say it's more about the SNARK part than the ZK part. And for those of you who aren't so familiar with SNARKs, we'll define those a bit later on in the talk. But I'll start by giving you, or saying a few words about the general outline of the talk. So the goal is to give you a bit of an insight into ZK-SNARKs and also some of the implications that arise when you're using ZK-SNARKs. And although they are inherently mathematical, we then move on to looking at or defining SNARKs themselves. And from there we can look at the implications of these cryptographic techniques in the use of SNARKs. And then we'll end with looking at a particular performance bottleneck when creating proofs with ZK-SNARKs. So start with the cryptography. There are two fundamental cryptographic or types of cryptographic primitive in cryptography. You have symmetric algorithms and asymmetric algorithms. So a symmetric algorithm is one where the encryption key is typically the same as the decryption key. So if you know the encryption key, you therefore know the decryption key. And examples of symmetric ciphers include things like AES, which is a very widely used symmetric cipher. You've probably seen things saying we use AES 256. So that's a symmetric cipher. But there are plenty of other symmetric ciphers out there. DES is one, that's an older block cipher. There's plenty of examples. The other type of cryptographic primitive is what we call asymmetric algorithms. And here you have two keys. They are mathematically related to each other, but it's computationally infeasible to determine one key from the other key. So if you know the encryption key, it's computationally infeasible to work out the corresponding decryption key. So what that means is you can, in effect, allow one key to be public. So your encryption key can be public, so anybody can encrypt data using that public key, but only the party that knows the corresponding decryption key can decrypt. And some examples of asymmetric algorithms include things like DSA, or the digital signature algorithm, as Diffie-Hellman key exchange, and a few others and a few variations on these basic schemes. So just to summarize some of the different properties or characteristics of symmetric and asymmetric algorithms. In terms of speed, symmetric ciphers are generally fast and efficient, whereas the asymmetric algorithms tend to be slow because they're doing some quite complex mathematical computations. In terms of use cases, it is the symmetric ciphers that you use for encrypting data or large amounts of data. The asymmetric algorithms tend to be used for what we call key management purposes and also for signature schemes. So when I say you don't use asymmetric algorithms for encryption, key management is a type of encryption. It's typically going to encrypt a symmetric key using an asymmetric algorithm as a means of distributing that key to another party. But in terms of actually general data encryption, so you don't use the asymmetric key, you use the symmetric algorithms. And these two types have very different key distribution requirements. So for symmetric ciphers, you need secrecy on the key. It's a bit easier with asymmetric because one key can be public, so it's far easier to distribute that key. But there's still the question of you need to verify that key does belong to the party you think it belongs to. And there are structures that let you do this, things like PKI, public key infrastructure. And in terms of the number of such algorithms, there are many different types of symmetric cipher. If you know how to design these things, it's fairly easy to design a reasonably good cipher. But with the asymmetric or the public key algorithms, there's relatively few algorithms around that are in practical use. And we're going to focus here on asymmetric algorithms, and we're going to focus in particular on a particular type of asymmetric algorithm. So the definition at the top, if you're not into the maths, you don't need to know too much about that definition. You can kind of skip over it. But this is a fundamental or foundational operation in public key cryptography. And you take or define y as being g raised to some power s modulo a prime number p, a large prime number. And if you're not familiar with modular arithmetic, you can think of that as being a bit like a remainder. Compute g to the s, you divide by p, you take the remainder. You wouldn't do it that way in practice, but that's conceptually what it's achieving. Why this problem is good is that, or is interesting, is that given y, g, and p, it's computationally infeasible to determine s, provided this prime p is large enough. And by large enough, the current recommended minimum size for p is 2048 bits in length, so they are huge numbers to give you sufficient security. And this is the problem that defines or enables schemes like Diffie-Hellman and DSA. They're all built around this central problem we see here, this is discrete log problem. Probably worth noting, though, that it's probably a bit of a bad habit. I talk about this as encrypting S. It's not strictly speaking encrypting S because you can't decrypt it. So it's more really of a hiding function than encrypting. But I tend to use the word encrypting, and I probably will do throughout this talk, just about out of habit, more than anything else. So within these discrete log type systems, there are two different mathematical structures that we can use. One's quite nice and straightforward. The one that we are interested in is not quite so nice, if you don't like the maths. And that's elliptic curve cryptography. So again, it's not so important to know the proper definition, but it's there for those who are interested. Elliptic curve is the set of all solutions to an equation of the form y squared equal x cubed plus ax plus b, which we define over a finite field. So solution, we mean a pair x and y that satisfies that equation for a given choice of a and b. And we call a solution to this equation a point on the curve. And this is perhaps the more general point even for the non-mathematicians. The important, or the interesting thing about elliptic curves is you can take 2 points on the curve, you can add them together using a special type of addition to obtain a third point on the curve. Or if like, you'd add 2 solutions to this equation and get a third solution to the equation. And that creates what mathematicians call a group. Doesn't matter what the definition of a group is, but this structure called a group. And that's the structure we need for schemes like Diffie-Hellman and DSA. So this gives us the structure that we need for those schemes to work, and where this discrete log problem is secure, and therefore you get these elliptic curve versions of schemes like Diffie-Hellman and DSA. When you're working with elliptic curves, the discrete logarithm problem is defined in a slightly different way. It's because this group is what's called an additive group. So we write it as got 2 points p and q, defined such that q is some scalar, a number, multiplying that point p. Then it's computationally infeasible to find s. But again, that's not so important from our perspective of this talk. What is perhaps more important is the 2 fundamental operations we have when we want to use or implement elliptic curves are point addition and scalar multiplication. So point addition is where you add 2 points together to get a third point. We've touched on that point already. And scalar multiplication is where you take a point and you multiply it by a scalar. In effect, you add the point p to itself s times. That's scalar multiplication by s. I mentioned earlier that asymmetric algorithms are slower, so just to give a feeling for how much slower elliptic curve operations are compared to, say, a symmetric cipher, we have a comparison here between one block of AES encryption and one EC scalar multiplication and also a EC point addition. The figures here are for when AES is accelerated in hardware, whereas the ECC is in software, which is perhaps not a fair comparison, but it's a very common thing. Most chips have AES built in hardware. That's quite normal these days, so it's a fair comparison in that sense. Now AES, some of you may know, comes with a choice of 3 different key sizes. 1 to 8-bit key, 192-bit key, or 256-bit key. Gone here, or chosen here, that the 1 to 8-bit key, because it's more of an equivalent security level to that offered by the elliptic curve BN254. And the curve BN254 that we use here as an example isn't the most efficient curve, but it's one that we will encounter later on when talking about SNARKs, so it makes sense to introduce it here. As we can see, AES is more than 30,000 times faster than one elliptic curve scalar multiplication. Even if you go to a software-only environment, it's still the case that AES is more than 2,000 times faster than one elliptic curve scalar multiplication. So there's a big difference between symmetric algorithms and what we encounter with elliptic curves. And here's the same numbers in a graphical form. It does highlight that the scalar multiplication is much slower than the point addition, but both operations are a lot slower than one AES encryption. What we've talked about so far are just a comparison with one symmetric encryption and these two operations in elliptic curves of scalar multiplication and point addition. If you want to do a fair comparison in terms of encryption, you need to use an algorithm or an EC algorithm that supports encryption. One is elliptic curve L-Gamal. So to encrypt data using elliptic curve L-Gamal, you need 2 scalar multiplications and 1 point addition. We have a comparison here which actually uses 2 AES blocks compared to one elliptic L-Gamal encryption. That's just because of the amount of data that you encrypt in one go. So 2 AES blocks is more or less the same size of data as one encryption with L-Gamal. So we can see that for proper encryption comparison, AES is still 30,000 times slower than one L-Gamal, EC L-Gamal encryption. So what we'll do now is we'll park the elliptic curves for the moment, move on to SNARKs. And we've mentioned zero knowledge a few times. Now this is the definition of ZK-SNARK. It stands for zero knowledge, succinct, non-interactive argument of knowledge. So the first part is zero knowledge that Anish mentioned earlier. It just allows you to prove that a statement is true without revealing any information. It could be that you know a secret or a set of secrets. It could be the input to some kind of one-way hash function, for example, with a known output. You can prove the corresponding input. We also have succinct, so the proofs are small and they're fixed size irrespective of the computation. That's one property of ZK-SNARKs. And non-interactive, so no interaction between the prover and the verifier. And they give the verifier the assurance that the prover does know the input. In terms of some uses, I should say zero knowledge has been around for quite a long time. It goes back to, I think, the 80s. And even my PhD thesis many years ago was on zero knowledge and threshold cryptography, which is a form of MPC. But back then it was more, so I guess, academic interest only. ZK proofs were more just showing that you could prove you knew a private key, for example. And that was about as far as they went. So zero knowledge has been around for a long time, but the use of circuits and more complex computations, that's the bit that's really come on in the last few years and changed things a lot. So in terms of some of the use cases, real-world use cases now for ZK-SNARKs, we have privacy-preserving protocols in DeFi. We have verifiable computation, which we kind of touched upon already. Things like roll-ups and anonymous credentials. So you can prove that you are, say you are an employee of a company, for example, therefore you have the right to access something, but you don't actually reveal your true identity. So lots of different things you can do with ZK proofs. So just to give an example with verifiable computation, we have a scenario here of a cloud server that performs some complex function. It could be some kind of data aggregation. It could be a machine learning training model. But the problem is, how do you, the receiver or the client, verify that computation has been done correctly? How do you trust it, in essence? And that's what ZK-SNARK will let you do. You prover can create this proof, the verifier can verify the proof, and that gives them confidence because of the properties that Anish mentioned earlier in terms of when he's defining SNARKs and zero knowledge, completeness, and so on. So that proves or gives the client the assurance that the computation has been done correctly. So moving on to connecting elliptic curves to SNARKs. For SNARKs, we need to encode the computation to some form that we can use to then create a proof. And what elliptic curves do is give you a mathematical foundation on which to build these proofs. And it comes down to what we call the homomorphic properties of elliptic curves. So elliptic curves, they're not homomorphic encryption schemes. You may have heard of FHE and so on. I'm not talking about that here. But the elliptic curves do still possess some homomorphic properties. And by homomorphic property, we mean that you can perform operations on encrypted data that mirrors the same operation on the plain text data. So rather than taking some encrypted data, decrypting it, performing your operation, and then re-encrypting it, you just did the operation on the encrypted data without having to decrypt. And the two operations that we have here are addition and scalar multiplication. So with addition, if you take the encrypted form of two values B and C, then we can compute the encrypted form of B plus C just by adding together, using this special type of point addition, the encrypted form of B and the encrypted form of C. And for scalar multiplication, if we give an encrypted form of a value B, then we can compute the encrypted form of B times C by taking the encrypted form of B and doing a scalar multiplication with the value of C. So those are good properties. We can do useful things with those, but first of all, we have to take the information used by the SNARK and put it into a form that we can then use to leverage these properties. So to do this, we need to take the SNARK information and we're going to convert that into a polynomial representation. So we'll say the SNARK works on a sequence of values, A0 up to AN. So each value is an integer within a certain range, defined by a finite field. This would include public inputs, outputs, some private values, and also all the intermediate values used within the computation. And we can map those values to a polynomial that we call T of S. So each of these numbers in the sequence becomes a coefficient in this polynomial. So A1, for example, becomes the coefficient of x to the power 1. A2 in the sequence becomes the coefficient of x squared, and so on. By putting it into this form, then we can then use algebraic techniques to construct a proof. So, okay, if anybody has any questions, by the way, let's go along. If you want to take a bit more time just to read a slide or something like that, perhaps, then just put your hand up. This slide does look a bit mathsy, but I'll kind of go through it slowly. So what we can do with elliptic curves is we can take a polynomial that represents the information used by the SNARK, and it's the polynomial T of x, and we can evaluate that at some secret value or secret unknown value S using only encrypted forms of S. So if you take the polynomial T of x, and that's evaluated at value x equals s, that becomes a0 plus a1 times s plus a2 times s squared and so on. We can then use the homomorphic properties we were just talking about to put that into encrypted form. It becomes a0 times some base point g plus a1 times the encrypted form of s plus a2 times the encrypted form of s squared and so on, which we can then rewrite as coefficient a times the point p0, where p is the encrypted form of s. Well, just I'll probably use a1 as an example. P1 is the encrypted form of s times g. P2 is the encrypted form of s squared times g, and so on. So how it does this isn't so important. I guess the takeaway is that you can use these points pi that are public information to enable you to compute the evaluation of this polynomial at this unknown value of s. And this is what we call a commitment to that polynomial. It's a commitment because having computed this commitment, you then cannot change any of the values or the coefficients of that polynomial. If any coefficient changes, it's likely to cause the evaluation of that polynomial to change. And you can't try and manipulate coefficients because you don't know the value of s. So therefore, once you created this, computed this, you are committed to that choice of polynomial, or if you like, that set of values a1 to an. So these homomorphic properties, they're good. Yeah, go ahead.
I have a question about commitment.
Yeah.
How are we sure that the commitment was created in the right way?
I think the proof would fail if you mess things around too much, because this is only one part of the overall proof system. Right. A whole set of these things have to be consistent when you come to the verification. Yep.
RPI generated using a trusted ceremony?
Yes.